Everything you will ever do is already fixed in the structure of reality. Your birth, this second, and your death all exist together inside one physical object, spacetime. That's what Einstein's relativity implies. Time is a dimension, not a flow, not a cosmic update. A dimension, like left-right or up-down. Physics bundles 3 dimensions of space with 1 dimension of time into spacetime. Every event is a point with 4 numbers, where and when. Take that seriously and you get the block universe. The universe is not playing out, it simply is. Past, present, and future are all parts of one 4-dimensional structure. Your whole life is not being written moment by moment. It's a complete line already embedded in that structure. Einstein knew how harsh that sounds. When a close friend died, he wrote that for people who really grasp physics, the difference between past, present, and future is only a stubborn illusion. He wasn't being poetic, he was stating what his own theory implies. Why does relativity push you here? Because it kills the idea of a universal now. We like to imagine one global moment really happening right now, everywhere, one cosmic clock. Relativity says that clock does not exist. Picture this. You sit on Earth basically at rest. Someone else flies past in a fast spaceship. You both agree on one event, you watching this video. Call that now. Then you both point to a distant star and ask, what is happening there right now? Relativity's answer is simple and brutal. You and the person on the ship do not agree. Because you're moving differently, you cut space-time into before, now, after in different ways. The events you call simultaneous with me watching this are not the ones they call simultaneous. At walking speeds, the mismatch is tiny. At airplane speeds, it's small but measurable. Near light speed, it becomes huge. Events you label in my future can land in their present. Events you think already happened can be in their future. So whose now is real? The only consistent answer, none of them. There is no built-in universal present. Now is not an objective feature of the universe. It depends on how you move. That alone wrecks the picture of a single slice of time sweeping forward. And this isn't just fancy geometry. The universe has hammered this into us in experiment after experiment. Take unstable particles. In accelerators, they live longer when we push them close to light speed than when they sit still. Their internal clocks tick slower compared to ours. That is time dilation, exactly as special relativity predicts. Cosmic ray muons show the same effect. They're created high in the atmosphere with a lifetime of about 2.2 microseconds at rest, far too short to cover the distance to the ground. Yet detectors at the surface see plenty of them. In our frame, the trip takes too long unless their clocks are running slow. In their frame, they live their normal lifetime and still make it because, for them, the distance is shorter. Different motions, different elapsed times, same physics. No master clock. To see the impact, switch to the space-time picture. Put time on the vertical axis, one direction in space on the horizontal. Every event is a dot. Your entire life is a continuous line on that diagram, your world line. You at 5, at 15, right now, and years from now are all different points on that same line. From the outside view of that diagram, the line is complete. All those points are there. From your own view, you only experience one point at a time. It feels like you move along the line. The space-time picture says the whole line is part of reality. There is no mechanism that brings the future into existence. It is already in the structure. At each event, light defines past and future light cones. Everything that could have affected that point and everything it can affect. Anything outside is causally disconnected, even though different observers slice now differently through the same fixed pattern. That's the block universe. The structure is fixed, our present is a local way of reading it. If this stayed in textbooks, you could ignore it. But your phone proves this picture is real every day. GPS only works because engineers treat time exactly the way relativity says. GPS satellites carry precise atomic clocks. They orbit high above Earth at several kilometers per second. Two things happen. Because they move fast, special relativity makes their clocks run slower than clocks on the ground. Because they sit higher and Earth's weaker gravity, general relativity makes their clocks run faster than ours. Add the numbers and you get a net drift of about 38 microseconds per day between a satellite clock and an Earth clock, if you don't correct it. Light travels about 300 meters in 1 microsecond. So 38 microseconds translates to errors of around 10 kilometers per day in your position. Quickly, your maps would be useless. So GPS is built with relativity baked in. The satellite clocks are set up so that once speed and gravity do their thing, they stay aligned with Earth time. Your phone is constantly using space-time to figure out where you are. If time were absolute, if there were one single clock for everyone, this would not be needed and GPS would fail. Put it all together. No universal now. Simultaneity depends on motion. Moving clocks tick differently. Experiments with particles and muons confirm it. GPS relies on it. Space-time diagrams show your life as one line in a four-dimensional structure. The simple idea of one flowing time is gone. The conclusion is severe. Your birth this exact second and your death are fixed locations in space-time. They're not popping in and out of existence. They're all there. You are not sliding along time. You are an object extended in time as much as in space. That raises a heavy question. If your whole life is already laid out in this block, if the future is as real as the past, then what does it mean to say that time passes? What does it mean to say one twin ages less than another, if all of it is already part of a single structure? To push that tension higher, we go straight into the most famous and most disturbing case of clocks disagreeing about reality. The twin who flies to the stars and comes back younger than the one who stayed home. Two twins, same age, same DNA, same birthday. One stays on Earth. The other climbs into a ship, fires the engines, and spends years flying close to the speed of light. They meet again. They compare ages. The traveler is younger by years. One body has literally lived less time than the other between the same two reunions. Relativity says this is not a trick, not a loophole, not science fiction. It is how space-time works. In the standard setup, the traveling twin accelerates hard, reaches a huge fraction of light speed, cruises, turns around, and comes back. For the stay-at-home twin, a lot of years pass. For the traveler, much less time passes. They follow different paths through space-time, so their clocks disagree on how long the trip really took. People call this the twin paradox, but there is no real paradox. The key is that the paths are not symmetric. The Earth twin stays almost inertial. The space twin turns, speeds up, slows down. The geometry of space-time gives a clear answer. The traveling twin's proper time, the time along their personal world line, is smaller. The equations are simple. The result is brutal. You might be tempted to say, nice thought experiment, but we can't actually do that. Wrong. We already see this effect. The scale is smaller, but the principle is the same. Astronauts on the International Space Station orbit Earth at about 7.7 kilometers per second. They move fast, and they're higher in Earth's gravity field. Their clocks run slightly slower because of speed, and slightly faster because of weaker gravity. Added up, and over a 6-month mission, they age microseconds less than people on the ground. Microseconds sound small, but it is real physical time. A career astronaut ends up measurably younger than their twin who stayed home. That should hit you. You like to think there is one answer to how long did this take. Relativity forces you to ask for which observer. There is no single universal number. Now drop from humans to particles. High above you, cosmic rays slam into atoms in the upper atmosphere and create muons. A muon is a particle similar to an electron but heavier. At rest, its average lifetime is about 2.2 microseconds. Even if it moved at the speed of light, 2.2 microseconds would only carry it a few hundred meters. The upper atmosphere is tens of kilometers up. Without relativity, almost none of those muons should reach the ground. But they do. Detectors at Earth's surface see showers of muons all the time. The only way to make that work is time dilation. From our point of view, the muons are moving close to light speed and their internal clocks are slowed down. Instead of having effectively 2.2 microseconds, they have many times that to live before decaying, enough to cross the whole distance. In the muon's own frame, nothing special happens. It still lives about 2.2 microseconds on average. It does not feel stretched out in time. For the muon, the atmosphere is length contracted, so the distance it has to cross is shorter. 2 frames, 2 stories, 1 consistent spacetime. There is no unique God's eye answer for how much time really passed. Maybe you still want to push this away. Particles, space stations, extreme speeds, too exotic. So take something boring, commercial airplanes. In the 1970s, the Heifel-Keating experiment put atomic clocks on passenger jets and flew them around the world, eastward and westward. Identical clocks stayed on the ground. When they compared them afterward, the flying clocks had lost or gained tens of nanoseconds relative to the ground clocks. That tiny shift matched the predictions of relativity once you accounted for speed and altitude. Tens of nanoseconds are microscopic, but the universe did not care about your feelings. It followed the equations exactly. Different paths through space-time produced different elapsed times. The clocks did not snap back into agreement. Reality allowed disagreement and stuck with it. Your own body is full of clocks like this. Your heartbeat, your neural firing, your chemical reactions, all are physical processes that measure time along your path. If your life and someone else's life are spent in slightly different motions and slightly different gravitational fields, your total experience time between birth and death will not match theirs exactly. Close, yes. Identical? No. This is the core rule. Every clock, every process, every person follows a path through space-time and accumulates its own proper time. Proper time is the time measured by the clock that moves with you. It is personal. It is not shared across the universe. That means when you say right now, you are talking about your own slice through space-time, not some global update the universe is doing. Someone far away, moving differently, will cut space-time into past, present, future in another way. Their now will include events that you call future and exclude events you call present. There is no master setting that makes one of you correct and the other wrong. So the idea that the universe is ticking forward together is false. There is no central cosmic clock. There is a fixed 4-dimensional spacetime, and each clock traces its own world line through it, picking up its own amount of time between 2 events. Time dilation is not time malfunctioning. It is time obeying the geometry of a static 4D structure. Once you accept that, the twin who comes back younger stops being a puzzle. You draw both world lines in the same spacetime, calculate the proper time along each between we separate and we reunite, and you get different numbers. The traveler simply has a shorter length of time along their path. That is the same basic pattern you saw with muons, with jets, with satellites, just turned up to human scale. All these mismatched clocks are telling you the same thing. There is no single shared time flowing through the universe. There are many times, one for each path. The block universe picture is not an extra philosophical layer. It is the simplest way to understand why these numbers line up in experiment after experiment. And now, the next step is harder. If motion alone can shrink or stretch your time, what happens when gravity itself starts to bend time? What happens when you stand deeper in a gravitational field and your clock slows compared to someone far away, and that difference is built into the shape of spacetime? You already saw speed rip time apart. Now gravity does the same thing, and it doesn't ask for permission. Here's the rule. The deeper you are in a gravitational field, the slower your time runs compared to someone higher up. Not slower as in feel slow. Slower as in your heart, your atoms, your aging, every process in your body ticks fewer times between the same 2 events. General relativity gives the reason in one sentence. Mass and energy curve spacetime. Curved spacetime tells matter how to move. Gravity is not a pull in the old sense. It's geometry, and when the geometry bends, it bends time too. Closer to a massive object, spacetime is more curved. The time part of spacetime gets stretched. A clock sitting deep in that curve accumulates less time than a clock far away. That is not a claim sitting on a blackboard. It has been hit with experiments again and again. Take the Pound-Rebka experiment. They use gamma rays, very high energy light, emitted at the bottom of a tower and detected at the top. If gravity affects time, light climbing out of Earth's field should lose a tiny bit of energy, which shows up as a slight shift in frequency, a gravitational redshift. The shift is small, but measurable. They saw it, exactly what general relativity said they should see. Light itself is telling you time is running differently at different heights. Now shrink the distance, forget towers, use meters, centimeters. Your head is higher than your feet. That means your head is in a slightly weaker gravitational field than your feet. According to general relativity, the clock in your head runs faster than the clock in your feet. That sounds like a bad joke until you realize labs have tested this with atomic clocks separated by tens of centimeters. Modern experiments put ultra-precise clocks on shelves at slightly different heights. After enough time, they drift apart by tiny but measurable amounts. Raise a clock by 30 centimeters and it ticks faster in a way that matches the equations. Move it back down and it falls back into the slower zone. Your body is literally stretched through a gradient of time. Over a human lifetime, the difference between your head and feet is small, but it is not zero. If you lie down for your entire life, you age slightly less than if you stand up. The universe is that strict. Now push gravity to the edge. Black holes. A black hole is a region where space-time is so curved that not even light can escape from inside a certain surface, the event horizon. Near that horizon, time dilation becomes extreme. For someone far away, watching you fall toward the black hole, your clock appears to slow down more and more. Your signals get stretched, redshifted, weaker. You seem to freeze, fading and crawling toward the horizon, but never quite crossing. From your own point of view, your proper time feels normal. Your heart beats normally. Your watch ticks normally. You fall through the horizon in a finite number of seconds. No drama in your personal time until tidal forces start tearing you apart. Two views, both allowed by the geometry, both talking about different slices of the same space-time. These objects are not theory decorations anymore. In 2019, the Event Horizon Telescope released the first direct image of the shadow of the supermassive black hole M87, a dark central region surrounded by a bright ring of infalling matter. In 2022, they did the same for the black hole at the center of our own galaxy, Sagittarius A. Those fuzzy rings are signals from matter in a region where time is already heavily distorted. Those photons have climbed out of a deep time well to reach us. Black holes are time dilation machines turned to maximum. Sit safely far away and watch someone approach the horizon. You see their time almost stop. Stay with them and you just fall. Gravity is not just bending their path, it is twisting what future even means near that object. Now link this back to something you already use, GPS. You heard this before, but now you can see the double hit. The satellites in the GPS constellation orbit high above Earth. Higher up means weaker gravity than on the ground, so their clocks run faster due to gravitational time dilation. But they are also moving fast, so special relativity makes their clocks run slower. Put the two effects together and the net result is this. Without correction, the satellite clocks would gain about 38 microseconds per day relative to clocks on Earth. That small mismatch becomes a disaster for positioning, turning into errors of kilometers per day. So the system is built from the ground up to include both special and general relativity, speed and gravity, motion and curvature. Every navigation app on your phone is a direct, daily demonstration that time does not tick uniformly in the universe. So where does that leave the picture of reality? Speed already forced you to accept that there is no universal time. Gravity takes that and engraves it into the geometry of the entire cosmos. Different places in a gravitational field have different clock rates. Space is not just bent. The way you slice space-time into now surfaces depends on where you are and how you move. In flat space-time, you could at least imagine a family of parallel now slices, even if no single one is special. In curved space-time, those slices twist and warp. Near a black hole, surfaces of equal time bend sharply compared to those in empty space. Future near a massive object is not aligned with future far away. They're all parts of the same 4D block, but the geometry is distorted. In the block universe view, gravity is the statement that the 4D block is not straight. It is curved. World lines bend, light cones tilt. The amount of proper time between two events depends on the path through that curved structure. Time dilation, whether from speed or gravity, is not time breaking. It is time obeying the shape of the block. So take stock. Your personal time is not universal. Your height changes your rate of aging. Your planet sits in a gravity well that slows all your clocks compared to deep space. Black holes carve extreme time pits into the structure of space-time. GPS quietly corrects for all of this to keep your map from going insane. And behind it all is one rigid message. There is no single shared timeline marching forward. There is a fixed four-dimensional geometry, and different paths through it give different times. That leaves a hard question hanging in the air. If the block is fixed and gravity and speed only change how we move inside it, who decides what can actually affect what? What sets the hard limit on which events can ever touch, send signals, or share cause and effect? To answer that, we have to draw sharp lines in space-time and admit that most of the universe is permanently out of reach. Right now, there are regions of the universe you can never touch, no matter what you do, no matter how long you wait. Not because you're weak, but because space-time itself has drawn hard lines and said, here, causality stops. Relativity turns that idea into a clean picture. Light cones. Take any event in space-time, say you watching this sentence. That event has a past light cone and a future light cone. The past light cone is everything that could possibly have an influence this moment, sending signals at or below the speed of light. The future light cone is everything you can possibly influence from here on out, again with signals that never outrun light. Anything inside those cones is causally connected. A flash of light, a radio wave, a particle, a shove, a decision, those can link events inside the cones. Anything outside? No chance. You can scream, you can fire rockets, you can pump infinite energy into your transmission ideas. If something is space-time separated in the wrong way, if it's outside your cones, there is simply no way to send or receive information. The geometry forbids it. The boundary of the cones is set by one speed, the speed of light in vacuum. C, about 300,000 kilometers per second. That number isn't just how fast light goes. It's the maximum speed at which any cause can reach any effect. All observers, no matter how they move, measure the same value for C. That's been hammered in by experiments like Michelson-Morley, and by everything we do with particle accelerators, lasers, and high-energy physics. You can't cheat this speed limit without wrecking the whole idea of before and after. Here's why faster-than-light signals are not just really fast, but destructive to the structure of time. Because different observers slice space-time differently into past, present, and future, allowing a signal to jump outside the light cone means that in some frames an effect can happen before its cause. You send a message, and in someone else's coordinates, they receive it before you send it. Chain a few of these moves together, and you can build closed loops where you warn yourself about something before it happens, or kill the cause with its own effect. Relativity doesn't just like that, it shuts it down. The only way to keep causality consistent for all observers is to lock in the rule, no influence travels outside the light cone. That's why c is not just a speed, it's the slope of the walls that protect cause and effect. Now look at your idea of the present. You think now means everything that is happening at the same time as you across the universe. That picture is wrong in two ways. First, as we already saw, simultaneity is relative. Different observers disagree about which events are now. Second, your actual physical access to reality is brutally limited by your light cones. What you can know right now is constrained by your past light cone. You only see things that have had time to send signals to you. The sun you see is the sun from about 8 minutes ago, because light takes 8 minutes to get here. A galaxy a billion light years away, you see it as it was a billion years ago, because that's how long its light spent inside your past light cone before hitting you. What you can change is limited by your future light cone. If you fire a laser, or send a spacecraft, or broadcast a message, the region that can ever be affected by that action is the inside of the future cone from this event. Everything outside is sealed off forever. No contact, no influence, no matter how advanced you become. So your present moment is not a clean universal plane. It's a local state inside a network of light cones. You are always living with incomplete information about space outside your past cone, and you can never have any control over regions outside your future cone. The idea that there is a shared absolute now for the universe is not just wrong, it's physically meaningless. There is, however, something shocking that all observers do share in their past: the afterglow of the Big Bang. Look at the sky with microwave telescopes and you see a faint, almost uniform glow, the cosmic microwave background, the CMB. It comes from a time about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. In cosmology, that surface is at redshift around 1100. It's a real physical layer in spacetime. Any observer anywhere in the universe, if they exist long enough and build good enough instruments, will see their own CMB. That surface sits inside the past light cone of every galaxy. In that sense, it's a shared past. But the way you slice it in time depends on your motion and your coordinates. The when of that surface is not universal. The fact that it's in your past cone is. So the light cones are doing several jobs at once. They define what can talk to what. They lay down strict limits on knowledge and influence. And they give you a cleaner way to think about the block universe. In the block picture, spacetime is a fixed 4D structure. Light cones carve that structure into 3 types of regions relative to any given event. Events in your past light cone, things that can affect you. Events in your future light cone, things that you can affect. And events forever outside both cones, things that are permanently disconnected from you. All 3 sets exist in the block. Past exists, future exists, elsewhere exists, but they are not equally reachable. Reality is not one big soup where everything can eventually talk to everything else. It is a structured network carved by light cones and constrained by a speed limit that cannot be broken. From your viewpoint, you feel a moving present. From the block viewpoint, your present is just a particular slice between your past and future cones, slowly climbing along your world line. You experience one chain of causes and effects. The full block contains every chain. Once you accept light cones, one question becomes unavoidable. If there is no universal present, and if light speed and cones dictate what can influence what, can we at least define some kind of cosmic time? Some average clock for the universe as a whole? Or is everything, down to the age of the universe, also just time according to someone? That question hits directly at how we even dare to say the universe is 13.8 billion years old, when every observer has their own time. You hear the universe is 13.8 billion years old, and it sounds final, like a single number written on the box of reality. But whose clock is that? Yours? An alien's? A galaxy falling into a black hole? And relativity, that question is dangerous because different observers disagree on time. Yet cosmology still dares to talk about one age for the whole universe. Here's how that trick works. On the largest scales, the universe looks roughly the same in every direction and from every typical place. Not perfectly, but statistically. Cosmology leans hard on that. We imagine an average rest frame where galaxies, on average, are just riding the expansion, not zipping around with big extra velocities. In that picture, we can define a special time coordinate, cosmic time. Cosmic time is the time measured by a clock that moves with this average cosmic flow. One of these ideal clocks sits with every co-moving observer, someone who isn't trying to rocket around, just drifting with the expansion of space. In the math, this is built into the FLW metric, the standard model of an expanding universe in general relativity. When cosmologists say the universe is about 13.8 billion years old, they mean 13.8 billion years of cosmic time have passed since the Big Bang, as measured by clocks riding with that average motion. It's not your personal time, it's the universe's picked out large-scale time coordinate. Now compare that to proper time. Proper time is the time along your own world line, measured by a clock you carry with you. That's your heartbeat time, your aging time. You and someone else can fight about whether two distant explosions were simultaneous, but you both will agree that your own wristwatch ticked a certain number of seconds between breakfast and dinner. That number is your proper time between those events. Relativity respects that. Each observer gets their own proper time. That's non-negotiable. What it refuses to give you is a global agreement about how to stitch all those personal times into one universal now. So you have two layers: cosmic time as an average large-scale coordinate tied to the expansion, and proper time as your personal clock. Both are real, but they are not the same thing. How do we actually read the cosmic clock? We use light and we use redshift. Light from distant galaxies gets stretched by the expansion of space. The wavelength gets longer, shifting toward the red. We label that with a number, z, the redshift. Z equals 0 means no stretching. Z equals 1 means the wavelength doubled. Z equals 10 means it got 11 times longer, and so on. That number is not just a color change, it's a timestamp. In our standard cosmological model, a higher redshift means we're seeing the galaxy at an earlier cosmic time. Light that left when the universe was a few 100 million years old arrives with huge redshift today. With the best telescopes, we see galaxies at Z greater than 10, meaning we're looking back to the first few 100 million years after the Big Bang, less than 5% of the universe's current age. So by collecting galaxies at different redshifts, we're basically sampling different cosmic times. It's not fiction, it's how observational cosmology works. You don't just say long ago. You say this galaxy at Z equals 7, this one at Z equals 3, and you plug that into the expansion history to get specific ages. On top of that, we map where those galaxies are in 3D space. Massive surveys like SDSS and DESI sweep huge chunks of the sky, measure the redshifts of millions of galaxies, and turn that into a giant 3D map. Filaments, clusters, voids, the cosmic web. If you stack those maps at different redshifts, you get something more. Not just 3D structure, but its evolution with time. In normal language, we see how the universe looked when it was young and smooth, how it looked later when structures were forming, and how it looks now with giant webs of galaxies. We treat it like a history, first this, then this, then this. But in the block universe view, you can flip that perspective. All those snapshots at different redshifts are not frames that are being created one after another. They are all different regions of 140 spacetime geometry. The early smooth universe, the clumpy present, the future thin cold universe, they all occupy different coordinates in the same block. The cosmic web you see in surveys is a 3D slice. Add cosmic time as a fourth dimension, and you get a 4D object, a growing, changing network in the usual dynamic picture, a fixed 4D structure in the block picture. The data do not care which interpretation you use. The equations describe a whole spacetime at once, and we walk through one path inside it. So where does that leave whose clock is right? Cosmic time is right for cosmology because it respects the large-scale symmetry of the universe. It's the natural coordinate to describe expansion, to say the universe is this old, to define things like the time of recombination or the time of reionization. It's the closest thing we have to an average clock of the universe. Your proper time is right for you because it is what you physically experience. No other clock has authority over your aging. If you spent billions of years orbiting a black hole in some weird trajectory, your personal time since the Big Bang could be vastly different from 13.8 billion years, while cosmic time still ticks along. There is no final, absolute answer that joins them into one sacred timeline. There's a 4D structure with many possible slicings. Cosmic time is one particular slicing that's extremely useful and tied to the large-scale flow of matter. Your now is another slice, a tilted slice tied to your motion, your location, your world line. The block universe absorbs both. It says the FLW cosmic time slices, your personal now slices, some aliens tilted slices near a black hole, all of them are ways of cutting the same 4D object. None of them is the one true present. They're just different coordinate choices on a space-time that does not care what you call now. That leads directly into a deeper problem. All these clocks, all these slices, all this geometry, fine. But they don't explain one thing you absolutely feel, that time has a direction. You remember yesterday, not tomorrow. You see eggs break, never unbreak. Physics keeps saying the block is static, but your experience screams flow and irreversibility. So the next question hits hard. If the block is fixed, and past and future both exist, why does time have an arrow at all? To answer that, we have to drag in entropy, the second law of thermodynamics, and the disturbing fact that the entire universe seems to have started in a freakishly special, low entropy state. You live in a universe where eggs only break, coffee only cools, smoke only spreads. You never see the reverse. Yet the fundamental laws of physics don't care about that direction at all. That mismatch is not a cute puzzle. It's a crack right through your idea of time. Look at the core equations. Newton's laws for motion, Maxwell's equations for electric and magnetic fields, Schrödinger's equation for quantum mechanics, Einstein's field equations for space-time. Flip time t to minus t, and with some sign tweaks, the laws still work. Run the movie backwards and the equations are fine with it. A broken glass flying up off the floor, reassembling in your hand. Air in a room spontaneously collecting into one corner. Heat flowing from cold objects into hot ones. The math does not forbid these processes in principle. But you never see them. Not once. Not in your kitchen. Not in any lab. Not in the entire history of recorded science. Forward in time, yes. Backward in time, no. So where does the arrow come from? The answer is entropy. The second law of thermodynamics says, in a closed system, entropy tends to increase, not decrease. Entropy is a measure of how many microscopic arrangements correspond to what you see macroscopically. More ways to be equals higher entropy. Here's the simple logic. There are usually far more disordered configurations than ordered ones. Imagine a box with gas in one half and vacuum in the other. Take away the barrier. The gas spreads out to fill the entire box. Why? Not because the molecules want to spread, but because there are vastly more ways for them to be all over the box than bunched neatly in one side. Technically, the reverse is allowed. All the molecules could happen to rush back into one half. But the number of microstates that do that is so tiny compared to the number that's spread everywhere that the probability is essentially zero on any human timescale. So you see one direction. Spread, mix, equalize. Entropy up. You can measure this in real experiments. Gas diffusion, heat flowing from hot metal into cold water, dye mixing into fluid. Every time, the large-scale pattern goes from special, ordered, low entropy to generic, messy, high entropy. Never the reverse. That one-way behavior is the arrow of time in practice. So the arrow is not in the microscopic equations. It's in the statistics of large numbers plus a critical assumption. The system started in a low entropy state. Now apply that to the entire universe. Look at the cosmic microwave background. It shows the universe when it was about 380,000 years old. Hot, dense, and extremely uniform. Tiny fluctuations, yes, but overall very smooth. That state is high entropy for normal matter and radiation. But in gravity, that smoothness is actually low entropy. Why? Because for gravity, clumpiness is higher entropy. A uniform gas under gravity is unstable. It wants to collapse, form stars, galaxies, black holes. There are far more ways for matter to be in complicated clump structures than in one almost perfectly smooth blob. So the early universe was in a very special, low gravitational entropy state. That's the key. The Big Bang didn't just launch expansion. It launched the universe in a freakishly ordered condition. From that point on, gravity plus thermodynamics drive everything toward higher entropy. Gas clouds collapsing, stars igniting, stars burning fuel, planets forming, life feeding on energy gradients, heat radiating into space. The arrow of time is basically the universe relaxing from that special initial condition toward more typical disordered states. Your whole life rides on that. You eat because there's a flow of usable energy from the sun to Earth and out into space. Your brain thinks because it burns fuel and dumps heat. Memory, decay, growth, evolution, these are all one-way processes tied to entropy increasing. Now connect this to why you remember the past, but not the future. Information about the past is stored in higher entropy records. Your brain stores patterns. Your phone stores photos. Rocks store fossils. Light bouncing around the universe carries imprints of what happened. All of these records increase entropy. Each time something is written into the world as a memory, microscopic details get scrambled, energy gets dumped, order gets diluted. The past has left traces because entropy has been increasing in that direction. There are many ways to encode what happened in messy final states. But there are no records of the future, because those high entropy states have not formed yet. The processes that will create those records haven't run. The scrambling hasn't happened. Nothing in the fundamental equation says you must only remember the past. The explanation is we are embedded in a universe with a low entropy boundary condition in what we call the past, and entropy increases away from it. Memory and records naturally point back toward that low entropy edge. So how does this fit with the block universe? In the block view, the entire history of entropy, from incredibly low near the Big Bang to incredibly high in the far future, is just a static gradient across spacetime. There is no cosmic slider moving from low to high. There is just a 4D structure in which one region has low entropy, later regions have higher entropy, and world lines thread through that gradient. Your feeling of time flowing from past to future is what it's like to move along a world line from low entropy regions to high entropy regions. You experience one direction because the structure you're part of is built that way. The block does not update. It already contains the full entropy profile. The arrow of time is not a moving cursor. It's a pattern in the geometry. From outside the block, you could label slices: early universe, smooth, low entropy; middle era, stars and galaxies, rising entropy; late universe, cold, thin, near heat death. All of those exist as different regions. From inside, you feel that as a story that runs one way, from simple to complex to exhausted. That kills one more illusion. Time doesn't flow because the universe is stepping forward. Time has an arrow because the universe's boundary conditions are absurdly special on one side of the block and generic on the other. Once you accept that, the next tension hits. If the block has a fixed entropy gradient, if the arrow is built into the structure, what happens when you add quantum mechanics on top, where systems can be in multiple states at once, and outcomes seem genuinely uncertain? If the future is already embedded in the block, do many possible futures exist? Or is there only one fixed chain of quantum events carved into space-time? You're told the future might already be fixed, like a finished space-time block, but quantum physics tells you the future is genuinely uncertain. Both cannot be literally true in the same way. So which story do you trust? The frozen block or the rolling dice? Quantum mechanics starts with something brutal. A system can be in multiple states at once. Not, we just don't know. Literally, both at once in the mathematics. That's superposition. You fire electrons at a barrier with two slits and catch them on a screen behind. If electrons were just little bullets, you'd get two bright bands. Instead, when both slits are open, you get an interference pattern, a series of bright and dark stripes. That pattern is the hallmark of waves combining, regions of high probability and low probability formed by wave-like interference. Push harder. Fire electrons one at a time. Wait for each one. They hit as individual dots on the screen. At first, the pattern looks random, but as you collect more and more hits, the same interference pattern slowly builds up. Each electron behaves like a wave in flight, passing through both slits in superposition, then lands as a single point. The statistics reveal the wave behavior.
Do it with photons, atoms, even big molecules. You get the same story. Quantum experiments are not rumors. They are standard lab work. Superposition is real in the sense that it makes correct predictions over and over again. Mathematically, this is driven by the wave function, the object that encodes all possible states of a system and their probabilities. The wave function evolves according to the Schrödinger equation. And here is the crucial point. That equation does not have a built-in arrow of time. If you know the wave function at one time, you can evolve it forwards or backwards. Time reversal is allowed. The core quantum dynamics are time-symmetric. So you have two things at once, a time-symmetric evolution and our experience that measurements produce definite outcomes and a clear before-after structure. Where does the direction come from? One standard answer is wave function collapse. In many textbook treatments, when you measure a quantum system, the wave function collapses from a spread-out superposition into a single eigenstate, one definite outcome. Before measurement, many options. After measurement, one result. That process is not described by Schrödinger's equation. It's added on top. And it does break time symmetry because it has a clear direction. You never see a definite result spontaneously explode back into a clean superposition of different possibilities. This is where interpretations of quantum mechanics fight. Many world says there is no collapse. The wave function never picks a single outcome. Instead, all possible outcomes occur, each in its own branch of a huge multiverse. When you measure, you split. There is one branch where you saw spin up and a branch where you saw spin down. Both are real. The block universe says something different. Each specific, complete history is one fixed 4D spacetime. Every measurement result along your world line is just one chain of events in that block. No branching needed inside a single block. There is one definite pattern of outcomes. You can combine those ideas into a harsher picture, a multiverse of blocks. Every possible way the quantum events could have played out corresponds to a different 4D spacetime. In that view, many worlds is not one block splitting. It's an ensemble of complete blocks, each with its own fixed history. You, in one block, experience exactly one timeline of outcomes. Then quantum experiments do something that looks even worse: delayed choice setups. In Wheeler's delayed choice experiment, you send a photon or another quantum particle toward an interferometer that can show wave-like interference or particle-like behavior depending on how you configure it. The twist: you choose the configuration after the photon has already passed some key part of the apparatus. Naively, it looks like your choice now decides whether the photon came by both paths or came by one path in the past. That sounds like backwards in time influence. Quantum eraser experiments push the same idea. You can erase or keep which path information after the particle has been detected, and the interference pattern appears or disappears when you sort the data. Here's the hard truth. These experiments do not actually change past events. They change which correlations you can see when you compare results. There is no real violation of causality. You never send a usable signal back in time. But they do smash your comfortable story about the photon having a single, clear history between source and detector. In the standard view, you're forced into statements like, the question, which path did it really take, is simply not well defined. That is not a satisfying sentence, but it's what the theory demands and the experiments support. Now tie this to your own timeline. From your point of view, at each quantum event, you see one result. You flip a quantum coin, you get heads or tails. You measure spin, you see up or down. You live one chain of outcomes. Your memories, your instruments, your body chemistry all record that specific sequence. That chain is your world line through a reality that has quantum uncertainty built in. In a block universe perspective, that entire chain, including all your future measurements, already sits in the space-time structure. Every dice roll, every decay event, every detector click along your world line has a fixed value at some point in the block. You don't know those values yet, but ignorance is not the same as non-existence. The block does not wait for you to collapse anything. It simply contains one consistent record of what happened, where, and when. If you combine this with many world-style thinking, you get an even colder picture. There may be blocks for every allowed quantum history. Your existence is one line in one block. Other versions of you run through other blocks where different results occurred. You never jump between them. You never feel the branching. You just experience one definite reality. So is the future open or closed? Operationally, for you, it is open. Quantum mechanics gives you probabilities, not certainties, for many processes. You can calculate that some event has a 30% chance or a 99.9% chance, but not this will happen. You live under that uncertainty. You plan under it. You gamble under it. In a block universe plus quantum view, one specific outcome will be the one etched into the structure along your world line. You don't know which one in advance. Your lack of knowledge lets you treat the future as genuinely uncertain, even if the block perspective treats it as already fixed. That tension between genuine unpredictability in practice and a fixed spacetime in principle does not go away easily. Physics has not fully resolved it. Different interpretations draw the line in different places, but none of them let you go back to the simple picture where the universe updates one frame at a time and the future literally doesn't exist yet. Now stack what you have. Relativity shreds at universal now, gravity works time, light cones fence off what can ever talk to what, entropy builds a one-way arrow, and quantum theory adds fundamental uncertainty on top of a spacetime that might already be complete. The next threat is bigger than particles and labs. The geometry of the entire universe itself cuts it into regions you can never reach, no matter how advanced you become, no matter how long you wait. There are boundaries in spacetime that permanently isolate entire chunks of reality. So the next question is unavoidable. In a universe with horizons that you can never cross, how much of the block are you actually allowed to see? Right now, you are already cut off from most of the universe. Not by technology, not by effort, but by the structure of spacetime itself. And that isolation will only get worse. Start with the most basic limit. The universe has a finite age and light has a finite speed. That means there is a maximum distance from which anything could possibly have influenced you since the Big Bang. That distance defines your particle horizon. The universe is about 13.8 billion years old in cosmic time. You might think the furthest stuff we can see should be about 13.8 billion light years away. It isn't. Because space has been expanding while light travels, the current distance to the most distant regions that have ever sent light to us is larger, on the order of 46 billion light years. That's the radius of the observable universe in co-moving coordinates. Anything farther than that has never had time to send us a signal since the Big Bang. No photon, no neutrino, no gravitation wave from those regions has had enough time to reach us. They exist as far as we can tell from the theory, but they are not part of our observable history. They are outside our past light cone. That's the first punch. Even in a perfectly calm universe with no accelerated expansion, there would always be a boundary between has touched us and has not touched us yet. Now add the second punch. The expansion of the universe is speeding up. Observations of distant Type 1a supernovae, plus measurements of the cosmic microwave background and large-scale structure, all point to the same conclusion. On the largest scales, the expansion is accelerating, driven by something we call dark energy. We don't know what dark energy really is. We do know what it does. It makes space itself expand faster over time. That changes the game. Because of this acceleration, there are galaxies whose light, emitted right now, will never reach us. Not in 10 billion years, not in a trillion, not ever. They are beyond what's called the cosmic event horizon. The particle horizon is about the past, how far light has had time to travel to us so far. The event horizon is about the future, which regions can ever send us light, no matter how long we wait. Accelerating expansion means the event horizon is finite. There are galaxies that are inside our past light cone today, but will be outside our future light cone forever from now on. We see them now, our descendants will not see them later. In space-time terms, those galaxies are sliding out of our future light cone. The world lines of their stars and our world line simply do not intersect beyond a certain point. Their future and our future both exist in the block, but there is no path for information to connect them after a certain cosmic time. Causal disconnection is baked in. You can watch this process in slow motion as redshift. As the universe expands, light from distant galaxies gets stretched to longer wavelengths. The farther away, the more expansion, the higher the redshift. Over time, as space keeps stretching faster, the same galaxy's light gets stretched more and more. Eventually, the wavelength becomes so long that the light slips out of any detector's range. Practical invisibility first, then, in the extreme far future, effective erasure. Over trillions of years, more and more galaxies cross that event horizon line. Their light takes longer and longer to reach us, gets more and more redshifted, and finally, never arrives. To any civilization living long enough in our local region, the sky will drain. The rich cosmic web, the deep field of galaxies, the structure we see now, will fade. They will see only the remains of our local group, and even that will change as galaxies merge. Eventually, for a far future observer, the universe will look like a cold, dark, almost empty space with maybe one massive galaxy and a bath of extremely stretched, nearly undetectable background radiation. They will have no direct observational access to the true cosmic history we can see today. They will not see the expansion. They will not see the CMB peak the way we do. The data will be gone. None of that means those other regions stopped existing. In the block universe view, today's busy, crowded cosmic web slice and those future lonely slices are both equally real parts of spacetime. The difference is which parts are causally connected to your world line. Horizons, particle and event, are just the boundaries in the 4D structure between can ever influence or be influenced and forever disconnected. The particle horizon wraps the part of the block that has already sent signals into your past light cone. The event horizon wraps the part that can ever send anything into your future light cone. Everything outside is part of the block, but not part of your causal story. So your position in the universe is worse than just small. You occupy a tiny world line inside a finite observable bubble embedded in a much larger space-time, and that bubble itself is shrinking in terms of what's dynamically relevant. Whole swaths of the block are, for you, permanently off-limits. Stack that on top of everything else: no universal now, warped time and gravity, light cones fencing off influence, entropy giving time an arrow, quantum theory adding fundamental randomness, and now cosmic expansion permanently isolating regions from one another. All of that is happening on gigantic scales, but there are places where space-time does something even more extreme on smaller scales. Places where time slows so violently that from far away you never see an object finish falling. Places where your own proper time marches steadily forward while the outside universe races into its future without you. Those places are black holes. And near them, your journey into the future can literally end inside someone else's future. Near a black hole, time doesn't just slow down, it rips apart. Close to a massive object, gravity is stronger at your feet than at your head. Near Earth, that difference is tiny. Near a stellar mass black hole, it's brutal. The gradient in gravity, tidal gravity, stretches you along the direction of the field and squeezes you sideways. That's spaghettification. Your body, your ship, your atoms pulled into a long, thin line. That's not just stretching in space, it's stretching in time. The time dilation between your head and your feet explodes. The clock at your feet, deeper in the gravity well, runs slower than the one at your head. Your own body spans a range of clock rates. The closer you get, the more extreme the difference, until the object you are made of is no longer intact. Now look at your fall from two viewpoints. From far away, watching you approach the event horizon, we see your signals slow and fade. The light coming from you gets redshifted. Each tick of your clock takes longer in our time. You dim, your signals stretch, your last frame lingers near the horizon. In our coordinates, you never quite cross. You appear to freeze arbitrarily close to the horizon, becoming fainter and more redshifted, effectively vanishing. From your viewpoint, none of that happens. You feel gravity pulling you in. You accelerate, the horizon approaches, and you cross it in a finite amount of your proper time. Your watch ticks normally, your heart beats normally, until tidal forces start to wreck you. You do not see yourself freeze. You fall through, and once you're inside, all paths lead deeper toward the singularity in your future. Both stories are true in their own frames. There's no trick. It's one space-time where different world lines slice events differently. The same geometry produces "they never cross" for the outside observer and "I crossed in seconds" for the infaller. That's how warped time becomes near a black hole. These objects are not just theoretical monsters. They move, orbit, and collide. When two black holes spiral into each other, space-time itself shakes. LIGO and Virgo have recorded this. In 2015, the first detection, GW 150914, was a direct hit. Two black holes around 30 solar masses each merged over a fraction of a second. A chunk of their mass, about 3 suns worth, was converted into gravitational waves. Those waves were distortions in spacetime, traveling at the speed of light, stretching and squeezing distances by less than the width of a proton over kilometers of detector arms. Still, we measured it. Each black hole merger is a violent rearrangement of spacetime geometry. You are not just watching objects moving inside spacetime, the fabric itself is being reconfigured. The gravitational waves carry information about the masses, spins, orbits, and the final remnant. They are pure, flying curvature. Then you hit the question almost everyone tries to dodge. What happens to information that falls into a black hole? Quantum field theory says black holes aren't perfectly black. They emit Hawking radiation, very faint, thermal radiation caused by quantum effects near the horizon. Over insane timescales, this radiation causes the black hole to lose mass and eventually evaporate. A stellar mass black hole takes something like 10 to the 67 years, a supermassive one far longer. Still, evaporation exists in the theory. Here's the problem. Hawking radiation, as originally described, looks thermal, random. If you throw in a detailed structured object, the outgoing radiation doesn't seem to carry that detailed information. If the black hole fully evaporates and the only thing left is featureless Hawking radiation, where did the information go? That would violate unitarity, a core principle of quantum mechanics that says information is never destroyed, only scrambled. This is the black hole information paradox. Does the information get lost? Is it somehow hidden in subtle correlations in the radiation? Is it stored on the horizon in some encoded form? Is our description of spacetime near the horizon incomplete? We do not have a fully settled answer, even today. Now plug this into the block universe.
In a 4D block, your entire journey into a black hole is one continuous world-line segment. You in deep space, you near the horizon, you crossing it, you stretched by tidal forces, you shredded into smaller pieces, your particles contributing to the mass and quantum state of the black hole, and later, those degrees of freedom bleeding out as Hawking radiation over trillions and trillions of years. That full sequence is one connected structure in spacetime. From the block viewpoint, there is no first it falls in, then we wait to see if information survives. The whole story, from infall to evaporation, is already part of the geometry. Either the block is built so that information is preserved in some encoded way, or it is built with genuine information destruction. The paradox is not about time evolution, it's about what pattern the 4D structure actually has. Near the horizon, the meaning of future and past also twists. Outside, your future points along a direction that never crosses the horizon. Inside, your future points inevitably toward the singularity. Directions that look like radial from far away become strongly time-like inside. What you call going inward outside the horizon becomes moving forward in time inside it. The labels future and past are tied to the local light cones, and those cones are tilted and squeezed by the gravity. So black holes are not just heavy objects, they are regions where time and space swap roles in extreme ways, where the outside universe might experience billions of years, while your proper time from horizon to singularity is seconds, where gravitational waves scream the story of merging horizons across the cosmos, where we still don't know exactly how reality handles information at the deepest level. Put all of this back into your own picture, you deciding whether to fall in or stay out. If you fall, your personal future ends inside someone else's distant future. If you stay, you watch them freeze and fade, but never see their end. Both paths exist as lines in spacetime. Both are real. That raises a nastier thought. If spacetime can bend and twist this much, can it loop? Can there be paths that start at some event, loop around through curved spacetime, and return to that same event? Closed time-like curves that are literally time loops. If those exist, then the block isn't just a rigid history. Parts of it could be knotted timelines where cause and effect chase their own tails. To find out how bad it could get, you have to talk about universes that allow time travel inside their geometry. You can walk forward and end up in your own past. Not in a story, not in a movie, but in real space-time geometry. General relativity allows that on paper. That's how extreme this theory is when you stop holding it back. Some exact solutions of Einstein's equations contain closed time-like curves. Time-like means a path you could travel if you moved slower than light. Closed means the path is a loop. Put those together and you get a route where you start at some event, move always into your local future, and eventually arrive back at the same event you started from. You never go faster than light. You never flip your arrow of time locally, yet globally you've circled back. The Gödel universe is one classic example. It's a rotating cosmological solution where, because of the global rotation of matter, the light cones tip over far enough that you can follow a time-like path that loops back. Some wormhole setups, if you accelerate one mouth and bring it back, also seem to allow CTCs. You enter the wormhole, come out the other end, and land in the past light cone of your own entry. On the page, the math behaves. The curvature is consistent, the energy momentum satisfies some conditions, or at least almost does. Einstein's equations say, okay, this is a valid spacetime. They do not scream illegal by themselves. Now you hit the immediate nightmare, the grandfather paradox. You go around a closed time-like curve, land in the past, and prevent your grandparents from meeting. If you succeed, you are never born. If you are never born, you never travel back. If you never travel back, your grandparents do meet, you are born, you travel back, and so on. Logical loop. No stable truth assignment. One way out is the Novikov self-consistency principle. It says, in any spacetime with CTCs, only globally self-consistent histories are allowed. You can travel back, but you cannot create a contradiction. Every event on the loop has to fit into one coherent story. So if you try to kill your grandfather, something always stops you. The gun jams, you change your mind, you hit the wrong person. The details can vary, but the overall loop stays consistent. Your grandparents survive, you are born, you eventually go back, and you create exactly the conditions that led to the same outcome. You don't get to rewrite the past. You become part of it. That's a very hard restriction. It means that in a universe with CTCs, free will in those regions is brutally constrained. You can only take actions that are part of a globally self-consistent 4D geometry. You feel like you could have done otherwise, but the global structure forbids any move that would create a paradox. That's one classical response. The other angle brings in quantum mechanics and Hawking's chronology protection idea. Hawking proposed the chronology protection conjecture that the laws of physics, especially quantum effects, will conspire to prevent the formation of CTCs in any realistic situation. Rough idea, as you try to create a region that would allow time loops, say by arranging wormholes, the quantum fields near that region blow up. Energy densities diverge, back reaction on spacetime becomes huge, and the would-be time machine destroys itself or gets cut off before a CTC region ever appears.
We don't have a full quantum gravity theory to prove this, but many toy calculations hint that quantum effects become violent near would-be closed time-like curves. The message is simple. Relativity's equations may allow CTCs, but the full quantum plus gravity system might slam the door shut anytime we try to open one. And crucially, we have zero experimental evidence for CTCs. No observed time travelers, no lab-made time loops, no signals that let you send information into your own past. Every test of causality so far shows a universe that behaves well. Effects follow causes inside light cones, not the other way around. So right now, closed time-like curves are mathematical toys. They tell you what general relativity can do in principle. They also tell you where the theory is probably incomplete, because once you allow loops, logic itself is at risk unless something enforces consistency. Now, drop them into the block universe. In a true block with CTCs, your entire looping life is just one static knot in spacetime. You don't create the loop, you are the loop. Every pass you make around that curve, every decision, every event is part of a single fixed 4D structure. There is no first time you travel back. There is no original unmodified past. The loop is part of the geometry from the start. In that picture, you never change the past because there is no separate pre-loop past to compare against. There is just the one space-time where your future self shows up in what you call the past, and always did. The distinction between before I change things and after I change things disappears. The block only has the self-consistent version. So the block universe doesn't just tolerate CTCs, it makes them conceptually cleaner. They're just weirdly shaped world lines. You feel a personal time flowing forward along the loop, but globally, you live on a closed curve that never rewrites anything. Then, you look at our actual universe. We see no causal chaos, no small-scale paradoxes, no macroscopic violations where someone obviously receives information from their own future. Gravitational wave signals from mergers, light from supernovae, the CMB, everything fits a picture with a well-behaved time direction and no loops. That strongly suggests one of two things. Either our universe simply doesn't have the global structure needed for CTCs, its large-scale geometry never tips the light cones over that far, or if CTC-friendly regions can form in principle, they're blocked,
hidden or quarantined in ways we cannot access, possibly by the same quantum effects Hawking was pointing at. From your standpoint, the message is harsh. The equations are willing to entertain time loops, but the actual universe you inhabit is ruthless about protecting causality. The block you live in looks globally ordered, not tangled. So step back and count. Relativity hints at loops, quantum hints at protection, observations show no time travel. That combination pushes you away from fantasy and back toward an even more unsettling place. A universe with one fixed history. No edits, no do-overs, and no loophole through the past. If there are no time machines to escape your timeline, and if spacetime is a fixed block, the next logical question is bigger and colder. How did this block start, and how does it end? Did the Big Bang, the era of stars, and the final death of everything all get written in from the beginning? To answer that, you have to zoom out from black holes and toy universes and look at the whole thing. The hot beginning, the expansion, the possible endings, and what it means if every phase is just another region of the same frozen spacetime. The universe did not just start. It ignited in a hot, dense state and then evolved into everything you see and everything you don't. And the same physics that tells you about that beginning also points to a cold, dead end. If the block universe is real, both the Big Bang and the final decay of everything are already fixed parts of the same structure. First, the beginning is not a guess. It's pinned down by hard evidence. Look at galaxies. Almost all of them are moving away from us, and the farther they are, the faster they recede. That's Hubble's law. Velocity is roughly proportional to distance. Run that backwards, and space was smaller in the past. Smaller, denser, hotter. Keep rewinding and you hit a state where the entire observable universe was crammed into a volume much smaller than it is now. You don't get that from one galaxy, you get it from the pattern across millions. Next, the sky is filled with a microwave glow coming from every direction, the cosmic microwave background. It's incredibly uniform, with a temperature of about 2.7 Kelvin, just above absolute zero, with tiny fluctuations. That radiation is leftover light from when the universe was about 380,000 years old and hot enough that matter and radiation were tightly coupled. As it expanded and cooled, the universe became transparent, and that light has been traveling since, stretched into microwaves. You see it as a fossil of the hot, dense past. Then look at the light elements. The amounts of hydrogen, helium, and a little bit of lithium in the universe match the predictions of Big Bang nucleosynthesis. If you take a hot early universe with a specific density and expansion rate and run nuclear reactions for the first few minutes, you get exactly the mix we observe. That is a narrow target. The theory hits it. So you have three independent nails: expansion, CMB, and primordial element abundances. Together, they lock in the picture of a hot, dense beginning. The universe used to be radically different. It had a real origin in time, at least in the sense of there was a state beyond which our current description breaks down. That's already a lot, but early universe physics goes further and says the beginning had a prologue: inflation. Inflation is a period of extremely rapid exponential expansion in the first tiny fraction of a second. Space blew up in size by an insane factor in a microscopic time. Why add this violent episode? Because it solves specific problems. Why the universe looks so uniform in every direction, the horizon problem. Why space is so close to flat on large scales, the flatness problem. And why we see the pattern of tiny fluctuations we do in the CMB. Quantum fluctuations during inflation get stretched to cosmic scales and become the seeds for structure. The predicted pattern of these fluctuations is nearly scale invariant, roughly the same strength on different scales with a slight tilt. That's exactly what we measure in the CMB temperature variations. It's not perfect yet, but the match is strong enough that inflation, or something very much like it, is hard to avoid. So, the beginning is not just, there was a bang. It's, there was an early regime, possibly with inflation, then a hot plasma, then atoms, then stars and galaxies. All of it governed by general relativity plus quantum fields. Now, Turn the arrow the other way and ask, how does this universe end? Several possibilities exist in the equations. If the average density were high enough and dark energy behaved differently, the expansion could halt and reverse in a big crunch, everything recollapsing into a dense final state. If dark energy grows stronger over time, you could get a big rip. Expansion accelerates so violently that galaxies, stars, planets, and eventually atoms get torn apart. That's the extreme. But current data say something colder and quieter. Dark energy is roughly constant and dominates the energy budget. That points to a future where expansion continues forever, faster and faster on the largest scales. Structures that are gravitationally bound, like galaxies or clusters, stay together. Everything else drifts further and further apart. This is the Big Freeze. In the Big Freeze picture, star formation eventually stops. Stars use up their available gas. New stars stop forming after roughly 10 to the 14th years, around 100 trillion years. That's your era of light ending. After that, the universe is populated by long-lived dim red dwarfs, then white dwarfs, neutron stars, black holes, and cold remnants. Over even longer timescales, white dwarfs cool, neutron stars may decay, and black holes slowly evaporate through Hawking radiation. The evaporation of the biggest black holes takes something like 10 to the 100 years or more. That's a 1 followed by 100 zeros. After that epoch, if our understanding holds, you're left with a thin bath of low-energy particles and radiation. Maximum entropy. No free energy gradients left to drive processes, no chemistry, no stars, no life, no complex structures doing anything. Just heat death. Forward in ordinary language, the universe runs out of useful fuel. It doesn't explode, it goes dark and quiet. Now drop that whole story into the block universe frame. In the block view, the Big Bang, the inflationary era, the hot plasma phase, the age of stars and galaxies, the long dark era of degenerate matter, the black hole epoch, the final trickle of Hawking radiation, and the uniform near-empty heat death phase are all different regions of one 4D spacetime. None of them is more real than the others. They are just different coordinates in the same geometry. Your entire civilization, your planet, your star exist in one tiny temporal band, the star era. A very brief slice sandwiched between an almost unimaginably dense bright beginning and an unimaginably long cold end. On the timeline from t=0 to t to the 100 years or more, you live in a razor-thin segment near the early side of structure formation. In the block, that sliver is there, fixed, alongside epochs where nothing like you exists and never will. You experience this as we came from a bang and head toward a heat death. The block doesn't experience anything. It just is the whole story at once. The arrow from Big Bang to heat death is encoded as an entropy gradient along the time dimension. From our perspective, that gradient is a plot. Initial conditions, evolution, conclusion. From the block perspective, it's the static profile of entropy across spacetime. So you are not just small in space, you're small in time. Almost everything that exists in this spacetime is not your era. You live in a brief, active flash between two huge deserts, the unknown physics of the very early universe on one side and the empty cold on the other. That should break any romantic idea that time is made for you. The universe is not centered on your now. It's a structure where your now is a tiny local feature. The laws that describe its beginning and end don't need you. They don't care. And yet, inside that tiny bright band, your brain insists on feeling something very different. A moving present, a thick now, a flow. You don't feel like a fixed line in a block, you feel like a mind riding a wave. So the next hard step is this. If the block is static, and the whole history is already there, why does your brain experience a flowing time at all? What is it about your nervous system that manufactures this illusion of now in a universe that doesn't have a global now? To answer that, you have to stop looking outward at galaxies and start looking inward at the way your brain slices and edits reality. Your sense of now is late, edited, and partly fake. It feels sharp and immediate. It isn't. Your brain is buffering reality. Neuroscience shows that what you experience as the present is built over a small time window, tens to hundreds of milliseconds, where your brain waits, gathers signals, and then decides this is what just happened. You are always slightly behind the real physical events. You can see this in reaction times. A light flashes, you hit a button. The gap is on the order of a couple hundred milliseconds. That's not just muscle delay, it's perception, decision, motor planning. Your brain is not a real-time feed. It's a slow, noisy system pretending to be instant. Temporal illusions expose the lie. In temporal binding experiments, two events that happen at slightly different times can be perceived as simultaneous if the brain decides they belong together. Or two events that are truly simultaneous can be perceived as offset if the brain has a reason to separate them. Your inner timeline is not a faithful printout. It's a heavily processed summary. Now run Einstein's train and lightning idea inside your skull. Imagine you're standing in the middle of a train car, and lightning strikes the front and the back at what the train's frame calls the same time. Light from both ends travels towards you. If it reaches your eyes together, your brain concludes those strikes were simultaneous. But here's the problem. That conclusion assumes equal path lengths, equal speeds, equal processing. In reality, neural signals take different routes, have different delays, and are processed differently. Your brain smooths over all of that and gives you one verdict. These happened at once, or this came first. You do this all the time. When sound and vision line up, like seeing someone speak and hearing their voice, you treat them as one event, even though the signals arrive at different times and are processed at different speeds. Your nervous system stretches and compresses small time differences to make a coherent story. That's temporal binding in your daily life. Outside your immediate body and its near environment, now is even more guesswork. Light from the moon takes about a second. From the sun, 8 minutes. From a distant galaxy, millions or billions of years. When you say what's happening right now over there, you are mixing delayed signals with assumptions and calling the result present. Physics already killed the idea of a universal now. Your brain just ignores that and manufactures a local one. Some models go even further and say you are not just living in the past, you are also constantly predicting the near future. Predictive processing says the brain is a prediction engine. It generates expectations about what will happen next, compares incoming signals to those predictions, and updates. That means a chunk of what you perceive is actually best guesses, filled in before the raw data fully lands. Your conscious experience might be a smoothed out, slightly delayed reconstruction that already includes a cleaned up version of the just future your brain expected. You don't see raw data. You see the brain's best model over a short time window, a mix of old signals, fresh signals, and predictions that survived error correction. It feels continuous and immediate only because your brain hides the stitching. This kills the idea that your present moment is some direct contact with reality's true now. There is no global now. There is your local, biological now. The state of your nervous system as it integrates and predicts over a small slice of its world line. That local now is real in a practical sense. It controls your actions. It shapes what you remember. It anchors your feeling of being a self moving through time. But it is not a property of the universe.
It is a feature of an information processing organ built out of slow, wet neurons. The brain has hard limits: finite speed of signals along axons, limited bandwidth in each synapse, constraints on how much detail it can track. So it does what it can: compresses, aligns, and narrates. It takes one path through spacetime, your world line, and summarizes a segment of it as, "This is me right now experiencing the flow of time." That story is strong enough to override what physics is telling you. Your brain insists, the past is gone, the future doesn't exist, only this instant is real. Physics answers, all those instants are just different locations along your world line in a 4D block. Your brain is zoomed in so tightly that it mistakes its own processing window for a fundamental structure of reality. In the block universe picture, every brain state you will ever have is already a point in spacetime. Each one has its own integrated now, its own buffer of processed inputs and predictions. The sense of flow comes from the fact that these brain states line up along your world line in order of increasing proper time, each one containing memories of earlier ones and none containing memories of later ones. You don't move through time. You are a sequence of brain states, each one convinced it is the present. The illusion of movement is built into how those states are wired. Past information stored, future information missing, predictions always aimed one way. That's the final twist. Your most basic feeling, that you are a single conscious self riding a moving present, is just what it feels like from the inside when a biological machine walks along a fixed track in spacetime and continuously rebuilds a story about itself. So stack everything now. Relativity kills a universal now. Gravity bends time. Light cones restrict causality. Entropy gives time a direction. Quantum mechanics injects uncertainty. Cosmology pins down a beginning and a cold end. Your brain fakes a present to cope with all this. That sets up the gut-level question you can't dodge anymore. If the future already exists in this block, and your brain is just reading it slice by slice, where does that leave your choices? Do you actually decide anything, or are your decisions just fixed features of a frozen spacetime pattern that happens to feel like agency from the inside? To hit that head-on, you have to tackle free will in a universe that might already be fully written. If the future already exists, what are you actually choosing? That's the hit. In a block universe, every "I'll do this instead" moment is already baked into the 4D pattern. The laws of physics plus the initial conditions spit out one specific space-time history. Your whole life is part of that single history, not something being written in real time. Take the hard version. Imagine the laws are fully deterministic at the fundamental level. Given the exact state of the universe at some early time, the equations fix everything that happens afterward. In the block view, that's just saying there is one four-dimensional spacetime that solves those equations with those starting conditions. No branching, no multiple actual futures. One. Your actions are in there. Every yes, every no. Every time you stayed, every time you left. Your preferences, your habits, your impulses, your rational arguments to yourself. All of it. Whatever you will do tomorrow is already a part of that structure. You just haven't reached that slice along your world line yet. That feels like a prison. You want to think, I could choose differently, but in a block universe with deterministic laws, there simply is no version of you in this space-time that does otherwise at that point. There's exactly one. So, does that kill free will? Depends what you mean by free. One philosophical move is compatibilism. It says, free will is not about breaking the laws of physics. It's about acting according to your desires, reasons, and values without external coercion. On that view, you have free will if, when you decide, the decision comes from your own internal processes, not from a gun to your head or a brain zap. In a block universe, that's still true. You are not a spectator strapped to a pre-written movie.
You are part of the machinery that produces the movie. The block includes a chunk of spacetime where your brain weighs options, simulates outcomes, feels conflict, and finally lands on one choice. That process is the decision. You didn't step outside the block to choose. You never could. But you are the piece of the block that implements the decision-making. Saying the block makes you choose X is just another way of saying you, as a physical system, choose X inside that block. The two are the same fact described at different levels. That math-level determinism is one side. Then quantum mechanics walks in and says, not so fast. At the quantum level, processes can be genuinely random in the sense that the theory only gives probabilities, not definite outcomes, even with perfect knowledge of the state. Radioactive decay, certain measurement outcomes, scattering events, these look intrinsically probabilistic. Some people grab that and say, here's the escape. Quantum randomness breaks strict determinism. The future is not fully fixed. But be careful. Randomness is not control. If a random quantum event flips a neuron in your brain and makes you raise your hand instead of not raising it, that doesn't make you more free. It just adds noise. A decision driven by a dice roll in your head is not more yours than a decision driven by your stable reasons and character. So, quantum randomness might mean the block is not determined by a simple set of classical initial conditions. It might mean that, at the deepest level, the block is picked from a probability distribution of possible space-time histories. But once you look at any one finished block, that history is still fixed. Inside that history, every quantum event has a definite outcome at some location in space-time. The randomness lives in which block becomes actual, not in your moment-to-moment feeling of choice. From a physics point of view, you are not a single point. You are a pattern spread out in spacetime, a network of brain states, bodily states, actions, and effects. That pattern has structure, memories, beliefs, habits, goals. When you decide, what's really happening is that one configuration of that pattern leads causally to another. Synapses fire, circuits light up, behaviors follow. Your future actions in the block are fixed in the sense that they have definite values at definite coordinates, but they are not uncaused. They are caused by earlier parts of the same pattern. Your upbringing, your experiences, your current mood, your logic, your emotional reactions. If someone asks, why did you do that? There will be an answer in terms of your reasons and states, not in terms of, because the block said so. So the story looks like this. At the highest level, there is a static spacetime with one complete history. At the middle level, there is a chain of psychological states in your brain, each one shaped by the ones before. At the first-person level, you experience that chain as choosing, deliberating, regretting, committing. All three descriptions talk about the same thing. The dread comes from feeling erased, like in a block universe nothing matters because it's all already there. But that's the wrong comparison. The alternative is not block versus magic. It's block plus laws versus what? A universe that updates in time but still follows strict laws from definite starting conditions doesn't give you any more literal wiggle room. It just hides the whole history from view. Meaning doesn't come from metaphysical flexibility. It comes from what actually happens. In the block universe, the version of you that tried, that refused, that helped, that built something, is not less real because their actions were part of the structure from the start. They are exactly as real as any black hole, any galaxy, any Big Bang. Your choices are not cosmic exceptions. They are how one small region of the universe, your brain, implements complex, value-laden decisions. If the block is real, then every moment you ever push back, every time you learn, every time you care about something other than yourself, those patterns are etched into the space-time fabric permanently. They cannot be undone. They are there. You may not like that the future is fixed, but if it is, then the fact that there is a version of you that does the hard thing anyway is not meaningless. It's the opposite. It means that in the one history this universe actually has, that person exists. That line was drawn. Still, the discomfort is huge. So some people just reject the block idea entirely. They say, no, only the present is real. Or the past and present exist, but the future doesn't exist yet. Or space-time itself is growing, not fixed. If the block view is this harsh, are there serious alternatives? Or are we just making ourselves feel better with pictures that quietly contradict relativity? To answer that, you have to put the block side by side with other models of time, presentism, growing block, evolving spacetime, and see if any of them can survive the physics you've already seen. Maybe the block universe is just a clever picture. Maybe it's only a map, not the territory. Maybe only this instant is real and everything else is a story. A lot of people want that to be true. The problem is relativity fights it every step of the way. Start with presentism. Presentism says only the present exists. The past is gone. The future is unreal. Reality is a single 3D slice updating moment by moment. That feels right. It matches how your brain talks to you. This is now. Everything else is memory or fantasy.
But the second you bring in special relativity, you smash into a wall. The present for whom? Because there is no absolute simultaneity. Two observers moving relative to each other cut spacetime into now slices differently. Events that are simultaneous in your frame will not be simultaneous in theirs. If presentism says only the events on the one true present slice are real, whose slice is it? If you try to say there is a hidden absolute frame, a cosmic true now, you are going beyond relativity. You're adding extra structure the theory doesn't need and experiments don't show. All the evidence so far says all inertial frames are equally valid. Physics doesn't pick a favorite. So strict presentism doesn't just feel a bit off, it directly collides with the core symmetry of relativity. To save it, you have to sneak in a special preferred frame, something the theory has gone out of its way not to include. Next idea, growing block. The growing block view says the past and present exist, but the future doesn't yet. The universe is a 4D block that is still under construction. New slices of time get added at the leading edge as now moves forward. Think of it as a scroll that keeps being written. That sounds like a compromise. You keep the reality of the past while allowing the future to be open. But again, relativity hits you. If spacetime grows by adding new slices, you need a rule about which slices and in what order. Which three-dimensional now is the one that just got added? In relativity, different observers disagree on which events are simultaneous, so they disagree on which slice should count as the present boundary of the block. To make a growing block work, you either have to pick a preferred slicing, an absolute cosmic time that says this is the real now, all others are illusions, or you have to invent a more complicated growth rule that somehow respects all frames at once. So far, there's no clean, widely accepted way to do that without breaking the spirit of relativity. Some physicists and philosophers try a more subtle move, the evolving block. In evolving block models, spacetime is still a 4D object, but not all of it exists yet. The block grows along some time parameter, adding new 4D chunks as the universe evolves, while already formed regions remain fixed. Once a region is added, it's like regular block spacetime. The future region is not there until it comes into being. These models try to respect the geometry of relativity while keeping a real sense of becoming. They want both, the nice 4D math and a genuine ontological difference between past and future. The difficulty is the same at the core. Relativity treats spacetime as a whole solution. Its equations don't naturally talk about adding slices. They describe entire spacetimes as objects that satisfy the field equations. When you solve them, you get a global structure, not a movie that the universe steps through one frame at a time. General relativity doesn't ask, what is the universe doing right now? It asks, what 4D geometry and matter distribution solve these equations? You can slice that geometry into nows however you like afterward,
But that's a coordinate choice, not a physical growth process written in the math. On the empirical side, our observations don't currently distinguish cleanly between a static block, a growing block, or an evolving block. All three can be made to reproduce the same measurable predictions about light, gravity, expansion, and so on, at least in broad outline. They differ in what they say is really happening behind the scenes. That makes this partly a matter of interpretation. So why does the pure block view keep pulling people back even when it's psychologically brutal? Because it fits the structure of relativity with the least extra baggage. It takes the math at face value. Spacetime is a four-dimensional manifold with a metric, matter fields, and a solution that covers all events. No privilege present, no growth law, no hidden time parameter. Just the geometry and its contents. It explains cleanly why different observers' nows are equally valid. There simply is no unique global present baked into the universe. Now is a local slice associated with a particular observer's world line. That's it. It meshes naturally with light cones, time dilation, gravitational redshift, cosmic horizons, and all the other weirdness you've already seen. Those are easy to picture if you treat spacetime as a fixed structure. They become messier if you insist reality is literally updating one shared moment at a time. The cost is emotional, not mathematical. The block view attacks two things humans cling to, a flowing present and a truly open future. It says the flow is your brain's construction. The openness is your ignorance. The universe itself is a single spacetime history that simply exists. Alternative views try to protect those intuitions. Presentism says only the present is real. Growing block says the future isn't real yet. Evolving block says space-time grows. But once you push them against the hard edges of relativity, something snaps. You either sneak in a hidden preferred frame, or a mysterious growth law, or extra structure the equations never asked for. That doesn't mean the block universe is proven. It means that, given what we know, it is the cleanest, most rootless way to make sense of relativity's geometry. It is the model you get when you stop trying to save your gut feelings and just let the math speak. So you end up here. Either time really flows and we're missing some deep new physics that reintroduces an objective present and an evolving universe, or the static block is closer to the truth in your experience of flow is a local illusion on top of a frozen structure. If the second option is right, then the picture of you changes completely. You're not a point moving along a line. You are a whole line, one extended object in spacetime, from birth to death, as real and fixed as a mountain is in space. To see what that actually means, not in equations but in terms of your life, you have to draw the final picture. Your world line in the cosmic atlas, your past and future as coordinates, and what it means to be a thread sewn into a 4D universe that never moves. Right now you feel like a point, one instant, one version of you sitting here watching this. Physics says that's not the full story. In spacetime, you are not a point. You are a line. Picture the universe as an atlas. Each page is a slice of time. On one page, you see galaxy clusters. On another, young stars forming. On another, Earth cooling, oceans forming, life crawling out. On the pages near now, you see cities, satellites, servers, and you staring at a screen. Now, stack all the pages. Don't think of them as separate moments. Think of them as cross-sections of one 4D object. All the galaxies trace long curves through that object. Stars trace shorter ones. Planets wind around stars. Spacecraft arc through the solar system. And your life, from birth to death, is one thin, continuous world line running through that same structure. That's what you are in space-time, a continuous path. A single extended track that includes every moment you call me. The 3-year-old you, who didn't understand any of this, is one point on that world line. The teenager you, who thought about the future and felt invincible, is another. The you right now, processing these words, is another. The you decades from now, wherever you end up, is another. All of them sit on the same curve in the block. Different coordinates, one object. From outside the block, there's no movement. The world line just is. From inside, each point on that line contains a brain state that thinks it is the present, with memories of earlier points and no access to later ones. That is what creates the feeling of moving through time. It's like this. Imagine a film reel already fully printed. Every frame exists. The beginning, the middle, the end. The projector doesn't create the frames, it reveals them in order. In the block universe, your world line is the whole reel. Your brain is the projector, locked to one frame at a time. But the frames don't wait to be printed. They're part of the space-time structure from the start. That sounds like it makes you a passive passenger? It doesn't. The block doesn't just include where you are, it includes what you do. Your struggles, your breakthroughs, your decisions, your failures, your recoveries. They're all parts of that world line. The argument you had and then made up from, the night you decided to quit something damaging, the day you chose to help someone when it cost you. Those aren't decorations on top of physics. They are what a certain region of space-time is physically doing at those coordinates. From the inside, you don't see this outcome was fixed. You see, I'm weighing options. I'm uncertain. I could do this or that. That experience is not a glitch. It's what it feels like to be a system whose future state is sensitive to a lot of internal variables, memories, values, thoughts, emotions. That sensitivity is part of the pattern the block contains. So no, the block universe does not turn you into a spectator. It makes you responsible. There is exactly one history in which your world line goes the way it does. If in that history, you act cowardly every time it matters, that's what the universe contains. If in that history, you slowly become braver, smarter, kinder, that's what the universe contains. You don't get to rewrite it from outside. You write it from inside by being the system that makes the choices. Now, zoom out hard. The universe is about 13.8 billion years old in cosmic time. The observable patch is more than 90 billion light years across in diameter. It contains hundreds of billions of galaxies, each with billions of stars. On that scale, your world line is microscopic, a hairline scratch on a skyscraper of space-time. Relativity does not care. That line is as real as any galaxy cluster's curve. The path of your life has the same ontological status as the orbit of Jupiter or the merger of black holes. It's part of the solution to the equations. It's baked into the geometry. It doesn't vanish because you feel small. Your entire civilization fits into a tiny band in cosmic time. The short era when stars are bright and planets are habitable. Before that, there was a hot, dense plasma. After that, there will be darkness and thin radiation. Your world line lives in that narrow, bright strip between deep past and deep future. Here's the final mental picture. Start with you in a room or on a bus or lying in bed watching this. Pull back to the building you're in. Pull back to your city. Pull back to the planet, clouds, satellites, the whole Earth turning. Pull back to the orbit of the moon. Then the solar system, Jupiter, Saturn, the Kuiper belt. Pull back again to the Milky Way, its spiral arms, its dark halo. Keep going. See the Milky Way as one point in the local group, then that group swallowed inside a cluster, then that cluster as a knot in the cosmic web, filaments and voids stretching out. All of that is your current now slice. Now flip the view. Instead of sliding your camera through space, slide it through space-time. Watch the stars form, burn, die. Watch galaxies collide and merge. Watch black holes grow and evaporate. Watch the cosmic web form and thin. Watch your planet emerge, cool, grow life, grow minds, grow you. That entire evolution is one 4D object. Then step even further back, in your imagination. Don't animate it, hold it still. One ghostly 4D block containing all of it at once. The first flash of the Big Bang, the birth of stars, their deaths, the appearance of you, your end, the collapse of structure, the slow slide into heat death. One impossible, frozen, complete sculpture of reality. Your world line is one fine curve drawn through that sculpture. It doesn't move. It doesn't need to. It already includes every moment you will ever call now. The shot conclusion is simple and brutal. You're not moving through time. You're the way time looks from the inside. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.